So DMA and UART, that is the direct memory access. This is universal asynchronous receiver transmitter. Let's see now DMA. So DMA, you will be able to understand at least some idea about DMA, how the data transfer occurs by using this DMA between memory to memory, or moving the data from flash memory to embedded SRAM, and so on. So because inside the microcontroller there are so many blocks, I already mentioned the purpose of the DMA is we are not using the CPU resource, but we still transfer the data from between different blocks. Let's see here. First, what is direct memory access? So DMA or direct memory access, from the name itself you can understand directly we are accessing the memory. So DMA is a feature in microcontroller that allows to perform data transfer between memory and memory, memory and peripheral. Peripheral means it can be a timer or ADC or any other peripheral, or peripheral and peripheral. So it helps to transfer the data between these blocks without using CPU resource. So you do not really use the CPU for this data transfer purpose, but this DMA is giving the control. So why memory transfer without using CPU as a resource? So why we need to do the data transfer without using the CPU? Because let us say if you transfer large amount of data continuously from maybe from one memory to another memory, or from one memory to peripheral, then the CPU will get engaged or it will stuck at data transfer. So CPU will be very busy only to handle this large amount of data transfer. So, but it will not focus on the data computation. But the main purpose of using the CPU is the CPU should handle the data computation. So whether whatever the operations, the addition or multiplication or division, or because everything is based on these operations, comparison, so on, so on. So if CPU is not focusing on the computation and if it focus on the data transfer, then the CPU will be hanged and you as a user, you need to wait for a long time. But in practical, do you have patience to wait? We do not really want to wait. Actually, when we click something, we want the result immediately. We do not want to wait. So we want very fast operation, high performance we expect from the CPU. So in that kind of situations, we need to have some new logic to handle these data transfers within the microcontroller without using CPU. For that purpose, we use this DMA. So DMA is very useful for direct data transfer without using CPU. Okay, so for example, this F103, it has two DMA, and DMA1 has 7 channels and DMA2 has 5 channels. So it has two DMAs, each one has a different number of channels. So for example, if you are using L476, let's say you are not using this one, maybe in the project you are using L476. So in the L476, you have to know how many DMAs and each DMA has how many channels. You just go to the data sheet. I think we have already opened the data sheet today, I think. So let's see here, where is the DMA and how many channels we have. Let's go to the table of contents. Where is DMA? I think chapter 3. Yes, direct memory access is here in chapter 3. So in the DMA, you can see here how many number of, okay. So this L476, this is the L476, you can see here, it has two DMA controller and each one has 7 channels. DMA1 has 7 channels, DMA2 has 7 channels. So that is the difference between different microcontrollers. This is L476. Okay. So, but F103, it has 7 channels in DMA1 and 5 channels in DMA2. So request from peripherals is connected to OR gate. So here you can see there are so many interrupt signals coming from peripherals. These are connected to the OR gate. This is the OR gate. Remember, in the logic gates, what the OR gate will do. So you can have multiple inputs. You can have 2 inputs or 3 inputs or whatever the number of inputs, but you will have only one output. So when I have 0, 0, I will have 0. 0 plus 0 is 0. OR gate is doing the addition operation. And if you have 0, 1, 0 plus 1 is 1 at the output. If you have changed this one, the 1 here and 0 here, the same. If you have 1 and 1, then you will have 1 and then you will have a carry 1. Okay, so this is the purpose of the OR gate. So whatever the number of inputs you are giving, whatever the number of interrupt signals you are giving, maybe it's 3 or 5 or 10, but at the output you get only one enabled signal. So here we are getting just only single output because we are handling everything in terms of zeros and ones. Okay, so it means only one request will be enabled at a time per channel. So these are each one is called a channel. So we have multiple interrupt faced by each channel, and each channel will get, but enable only one interrupt. So of course you should recall the truth table of OR gate. So OR gate is a very simple one, 0, 0. These are the input A, B. Output is Y. 0, 0, 1 is 1, 1, 0 is 1, 1, 1 is 1, right? So, but this is only 2 input, but you can have multiple inputs. So OR gate handles hardware request and software request, called memory to memory mode, is also given to multiplexer. So you can give all the external interrupts or peripheral interrupt to this OR gate, and OR gate will enable only one interrupt at the output based on the priority, and then this will be given to the mux and the multiplexer, and the multiplexer will have the enable bit. So in this enable bit, based on the enable bit status, you were enabling only one at a time output. So for example, here I set up the enable bit as 0, 0, 0, 0, 0, and so on. Then this mux is off. So we don't get anything at the output of this mux. But I set up the enable bit as 1 here. Then I can get the output from only this mux, and I am giving here. Of course, I can also have more than one at a time. That is why we have the priority. NVIC is setting up the priority to your interrupts. Okay, so we can get sometimes interrupt from hardware. Sometimes we can also receive interrupt from software. Now let us see. Software priority is programmable, that you can do program. For example, the screensaver, it's an event. It's also an interrupt. And you can set up the priority either very high priority or medium priority or low priority. These are software based priorities. It's programmable and it's flexible. And hardware priority, this is mainly used when there are 2 or more DMA requests with the same software priority level. So that we know. So we have more than one DMA. We have the DMA 1 and DMA 2, and each one has several channels. If they come up with the same priority level, then we have to go to the sub priority. So the lowest channel number has the highest priority, that we know that 0 is the highest priority. And then when it goes 1, 2, 3, then the priority will move. And the DMA 1 controller has highest priority than DMA 2 controller. So if I receive the interrupt from DMA 1 and DMA 2 at the same time, then CPU will consider the interrupt from this DMA 1 as the first, because this one has the highest priority. You see the number is low. This is the 1 and this is 2. Whenever we have the small number, then we have the highest priority. So if we have another DMA, for example, if I have the DMA 0, then of course the CPU will consider the request from DMA 0 as the highest priority, and then this one will go. Okay, so these are this is about the DMA, and the DMA has the capability of generating DMA interrupts, which are can be a half transfer or transfer complete or transfer error. This is just like the communication protocol. So how the data can be transferred during the half transfer, maybe we get another highest priority, then we give the half transfer acknowledgement and they execute the highest priority first, and then we'll return back to this half transfer and then complete. So after the data transfer got complete, we get the data transfer complete acknowledgement. In case if any error occurs, then we get this flag, data transfer error flag. Okay, so these are about DMA interrupt. So the same now, every time we have to check this is everything's okay. Sysdig is enabled, and then we are checking the RCC, real-time crystal clock, that is okay. Now the pin, we are setting this pin number 6 in port B as the GPIO output. That is going to the red LED. This pin number 6 is driving this red LED, and that is the output signal. So then what we can see here, this pin number 8 is set up for the green LED, and you can set up whatever the pin you want, and then go to the clock configuration and then set up the maximum, and then you go to this GPIO again and you are checking the pins what you set. This is the pin number 6, so you can set up this output push pull mode, and this is the label is user label is red LED. Here you can see user label, and then you can go to the DMA mode. So this is the most important thing. Now in this at least in this part of the lecture, we are talking about the DMA. So then you go to this DMA mode, and then you can see memory to memory data transfer. So you are using the channel 1 from DMA 1. So we know there are two DMA controllers, 1 and 2, but we are using the controller 1. In the controller 1 has 7 channels, and we are taking the channel 1. The priority is low. And you want to transfer in terms of bytes or word, so you can select whatever you want. That's all about this, and then you can generate the C code, and then you can edit the C code, and whatever the time delay you want to set up, you can set up. So I think I don't need to play this one. I guess this is everything is about C code. And so what we are doing here is we are transferring some data from memory to memory without using the CPU resource.